Hey everyone, welcome back. Today we're going to be following up on the previous two videos I made where I shared with you a technique or a workflow that I've come up with for developing assembly language programs for the Commander X16 computer. And today we're going to be doing something pretty fun. We're going to be looking at printing text characters on the screen of the Commander X16. And actually we're going to be doing a bit of cheating. We're going to learn how to create our own user-defined graphics characters. So we're going to kind of sneak in some graphics as well. But mainly what we're going to do today is look at how we can print text characters on the screen of the Commander X16 computer. And it's going to be quite a long video today because there are several topics we need to discuss. We need to be familiar with several aspects of the Commander X16 computer in relation to exactly how it displays images on the screen. So we're going to go through those step by step, and we're going to really take our time and learn how to understand the different topics and aspects of the computer that we need to be familiar with in order to do what we want to do in printing these text characters to the screen. Although printing text characters on the screen might not seem that exciting, it will be pretty fun because we're going to be doing some modifications to those characters. We're going to be changing the attributes, including the size and the shape and the color and the position, and we're even going to, as I mentioned before, create our own user-defined graphics character. So it's going to be a pretty cool video today, although it's going to be long and in depth. We're going to do some fun stuff and we'll get into it right now. Alright, so let's go ahead and get started. And although today's video about printing text on the screen might not seem particularly exciting, I think it's actually really cool and interesting because we're going to be looking at various different techniques we can use, as well as we're going to be learning quite a bit about the Commander X16 itself and its display capabilities. And just to give you a bit of a heads up, here are some of the topics we're going to be looking at in today's video. So here I've just got a picture on the screen of the character set that comes pre-installed in the Commander X16 that we'll be using in today's video, as well as the sample kind of output that I've shown here of what we're going to be playing around with using the techniques that we're going to be covering today as well. So here are some of the topics we're going to be looking at. Of course, we're going to be looking at how we can print text on the screen. We're going to be taking a look at the character set, which you can see displayed on the screen right now actually. We're going to be seeing how we can reposition the text on the screen, as well as printing some control codes to not only display these characters on the screen, but also using some of the non-printable codes as well. We're going to be rescaling the text on the screen to change its size and dimensions. We're going to be looking at how we can scroll these images on the screen, and that's pretty cool as well, particularly for use with games. And we're going to be, of course, taking a look at the colors that we can use for printing these characters, as well as we're going to kind of cheat and take a look at creating some user-defined graphics characters that we can use in our games. So we're also kind of looking at displaying graphics in today's video, although of course it's based on text characters. If we redefine those text characters, then now we have some user-defined graphics we can play with as well. So let's go ahead and get started and take a look at the next slide. So the video today is going to be divided into three separate topics that we're going to be looking at. Number one is the display characteristics. And if we take a look over at the right side here, I've listed some of the characteristics we're going to be looking at, including the video layers that the Commander X16 uses for displaying images on the screen. We're going to be taking a look at the Tilemap because that's what we're going to be using for displaying characters on the screen. We're going to be taking a look at the video RAM or VRAM in the Commander X16 computer, as well as we're going to look at the tile patterns that are stored in memory, as well as the color palette to show us which colors we'll have available for printing our text characters. Now section number 2 is titled Configuration. This is where we take a look at how we can actually configure the Commander X16 computer for allowing it to display what we want it to display on the screen. It's actually quite a bit more involved than, for example, using BASIC to print text on the screen, or you might be familiar with just using a basic print statement. Well, with the Commander X16 computer, since it is so versatile and so powerful, we need to configure it and tell it exactly how we want it to display our images on the screen. So that's what we're going to be looking at in section 2 here, and some of the topics we'll be discussing will be the VRAM addressing or video RAM addressing. So we will understand how we can access the video RAM addresses that we will need to use in our programming today. we're going to take a look at the registers, which is how we actually configure the Commander X16 for printing our images on the screen, as well as we'll take a look at the different text modes that are available to us for printing our text characters. And then finally in section 3 here, which is labeled assembly programming, of course we're going to be creating an assembly language program, which is going to be using 65C02 assembly language instructions, because of course the Commander X16 uses a 65C02 processor. And so we're going to be taking a look at the main program sections in our assembly language program, as well as we're going to, of course, use that program and modify these different sections and subroutines in order to actually test out and execute some of the display features that we're going to be using today and experimenting with in today's video. Alright, so on the first slide here, what we want to take a look at is the concept of layers. The Commander X16 computer uses something called video layers, which is a way we can separate the different elements that we want to have displayed on the screen. The bottom layer, which I've shown here as the background layer, is the one that appears below all of the other layers. And we're not actually able to print any graphics or images or text directly to that background layer, but there is one aspect of the background we are able to modify, which is the color. So whichever color is showing on the background layer, the entire background will be displayed in that color, and that color will actually show through any layers above it that are either transparent or disabled. So if you think of sheets of clear plastic, these can represent the layers that appear on top of the background, and just like you would have a sheet of clear plastic sitting on your tabletop at home, whatever color your tabletop is, of course, will show through that clear plastic, and you'll be able to see that color through all of the layers of clear plastic that you might place on top of it. And then, of course, any areas of the clear plastic sheets that are covered with graphics or text images or other colors will block that background layer from showing through. So although we can't print any graphics on the background layer, we can change its color, and we're going to look at the layers that appear above it. So just keep in mind that although we can't do any direct graphic manipulation of the background layer, we can do one change to it, which is selecting which color we want it to show in. And that can be useful when that layer does show through the layers above it for any layers that are either disabled or areas of the above layers which are actually shown in transparent colors. And we will actually be using that technique in today's program as well. Okay, the next layer here is layer 0, and layer 0 is positioned above the background layer. So again, if we use the analogy of using plastic sheets of paper, and you can of course take a felt marker and draw images and text characters and whatever you want on this sheet of clear plastic. When you lay that sheet of clear plastic on your tabletop, then you're going to see the image that you've drawn positioned on top of your tabletop color, whatever the background color of your tabletop happens to be. So that is exactly the way that it works with the Commander X16 computer as well. Layer 0 will be the layer directly above the background, and so the images or the text characters that you print on that layer 0 will show in front of or on top of the background layer color. And over on the right here, my note indicates that the layer 0 can be either text or bitmap, which means we can use it for printing text characters, or we can use it for displaying graphics images. And of course, in today's video, we're going to be printing text characters, so we'll be using text mode layers in our video today. And then my next note here simply says that it is positioned above the background layer. All right, we'll take a look at our third layer here, which is layer 1. So this layer is positioned above layer 0. So similarly to our analogy before, if we're using a plastic sheet of paper that we're drawing an image on it, or we're printing characters on it with our felt marker, then whatever images or characters we print on layer 1 will show in front of or on top of the images and characters that are displayed on layer 0. And of course, both of these layers appear in front of the background layer. Now, one thing to take note of is there is, as we will be seeing later, a transparent color that we can use. So any areas that are transparent will show through whatever images or colors are located on the layer below them. So for example, if we have a layer 0 image where part of it is transparent, then those transparent areas will show whatever color is on the background, because the background is positioned below layer 0. And similarly with layer 1, if we have any parts of the layer 1 image which are transparent, then they will show through whatever is on layer 0 below layer 1. And if any parts of layer 0 and layer 1 are both transparent, then whatever color is showing on the background will show through both layers 0 and 1 if those areas on both layer 0 and 1 both happen to be transparent as well. So what is another way that we can see the background color on our video screen? Well, another technique we can use is by simply disabling the layers above it. So if layer 1 and layer 0, for example, are both disabled in this case, then even if there are images displayed on layer 0 and layer 1, if we disable those layers, then nothing is going to show up on the screen for those layers, and we're going to see the background layer below it. So we are able to enable or disable these layers independently, except for the background. Of course, the background is always enabled, but we are able to enable or disable layer 0 and layer 1 as we see fit. And if we take a look at my note on the right side here as well for layer 1, we can see it works exactly the same way as layer 0 in that it can be configured in either text mode or bitmap mode, and it is, as I just mentioned, positioned above layer 0. So anything we print on layer 1 will show on top of or above layer 0. All right, we'll go on to our next layer here, which is called the sprite layer. So the Commander X16 has a fantastic capability built into it, which is it uses built-in sprites, which means that we can configure our own sprites, which I'm sure you're already familiar with what a sprite is. It's an independently controlled little graphics entity, which can be controlled and positioned independently of the other sprites and the other characters and the other images on the other layers. So the Commander X16 computer, as we can see by my note on the right hand side here, it says it has up to 128 sprite layers, which means we can program up to 128 different sprite images in the Commander X16 computer, and each sprite image exists on its own layer. And then if we look at our note number 2 here, it says above, below, or between layers 0 and layer 1. So these individual sprite layers can exist either above layer 0 or layer 1, it can exist below layer 0 or layer 1, or they can exist in between layer 0 and layer 1. Of course, they can't exist below the background. The background is the very bottom layer, so all of the sprite layers have to exist somewhere above the background, but other than that, they're completely independently controllable and positionable, and they can be positioned independently in relation to the other layers 0 and layer 1. So you can decide which images or which sprites you want to appear in front of or behind which other layer you might be displaying on the screen, in this case layer 0 or layer 1. And as I just mentioned, they have to be positioned above the background layer. All the images and other layers need to be positioned above the background layer because the background layer is the bottom layer. But other than that, the sprite layers can be positioned above or below each other, as well as above or below the other layers 0 and 1. So in today's video, we're not going to be using any sprite images. We're just going to be strictly looking at character and text graphics on the screen today. So we're not going to be using any sprite layers in today's video. Okay, now we're going to move on to the concept of the tile map. So you may already be familiar with how a tile map works if you used it on other personal computers. Well, if you're not familiar with how a tile map works, this is something that can potentially be confusing, particularly in the way the tile map relates to the tile patterns, which we'll be looking at in a moment. So the way a tile map works is you can think of a tile map kind of like a Scrabble board. The board game Scrabble that you may be familiar with, it's essentially just a board that has a grid printed on top of it, and then you would have separate individual tiles which contain characters, alphabetic characters, that you would position on top of that board or on top of the grid. So it works very similarly in the Commander X16 computer, whereas each individual position on the tile map can be set to represent a tile that is programmed in the Commander X16 memory. So for example, if we have a character set of different tiles, and I'm just going to show you the character set for the Commander X16 computer, which is right here. You can see all of these characters that are shown on the screen now. These are already pre-programmed into the Commander X16 computer, and these are the character images or the character tiles that we can use for printing on the screen. But the way we actually print these on the screen is we need to insert these tiles into the tile map. So we're going to be making up a map that consists of these different tiles connected together. And so we're going to look at how we do that right now. So if I go back to my slide here, you can see that the tile map is made up of a grid, and each of these grid locations represents one character that can be printed in that location. And on the Commander X16 computer, the default resolution for this tile map is 1024 by 512 pixels, or 128 by 64 characters, and each character would be one tile. And as my note indicates over on the right here, the tile in this case would be made up of 8 by 8 pixels. Now, if you're familiar with other computers, for example, the Mattel Aquarius computer, if you want to position a character on the screen in a certain location, then you would simply take the code for that character and you would insert it into a memory location that corresponds to that location on the screen. Well, it works similarly on the Commander X16 computer. As you can think of, each of these character positions on the tile map are represented by a location in video memory. So in order to display a character on the screen, we need to put a value into these different video memory locations that represent the tile map. But instead of using the values that directly represent these characters themselves, what we're going to do is use pointers to the character tiles that are located somewhere else in memory. But before we take a look at that, let's go on to our next slide here and take a look at a different concept, which is the visible area of this tile map. So this can potentially be confusing for people if they assume that the entire tile map represents the visible area of the screen. Well, actually the tile map is larger than the visible area of the screen, which you can see here. The 1024 by 512 pixels, that is the size of the entire tile map, represented by this green outline here, whereas the visible area of the screen is only 640 by 480 pixels, which represents 80 by 60 character locations as opposed to the full 128 by 64 character locations. So what this means is we have our tile map, which is made up of address locations in video memory, and we put pointers in these different address locations to indicate which characters we want to populate on these different locations in our tile map. And then we have a window which provides us a visible area into that tile map. And you can think of this kind of like a window in your house. So for example, if you're in your living room in your house and you're looking out your window into your backyard, well, of course you can't see your entire backyard from inside your living room. You can only see what portion of the backyard is showing through your window. And as you reposition yourself inside your living room, you can look through the window and see different portions of your backyard. Well, it works exactly the same way here, whereas your backyard would be represented by the tile map, which is this green outline here, but the visible area of your backyard would be represented by this red outline here, which is essentially a window to see what is in your backyard. So this red outline here on the Commander X16 computer represents the visible area on the screen, which is your video monitor, and that visible area is going to show you a portion of the entire tile map, which is shown here outlined in green. So although we can program the entire tile map to contain whatever characters we want to be positioned in those different locations, only a certain portion of those characters will be visible on the screen in any one time. And if we take a look at my notes here on the right hand side, it says the visible area is 640 by 480 pixels, which contains 80 by 60 characters, and these characters are 8 by 8 tiles. And we'll see a bit later how it's possible to change the size of the tiles, but in this case we're going to be using tiles that are 8 by 8 pixels in size. And one cool thing about this feature is we can actually scroll this visible window. It is scrollable to show us different areas of the background tile map image. So we can program our tile map to contain whatever characters we want to be populated there, and then we can reposition this visible screen area over whichever location of the tile map we want. And we can do this on a pixel by pixel basis. So we don't actually have to scroll this visible area character by character. As we're going to see later, we can scroll it pixel by pixel, which is really cool, for example, in making games where you want to be able to scroll the background image. And as I said, we're going to be taking a look at that a bit later in our video when we actually create our program. All right, let's go on to our next slide here. And this slide has quite a bit of information on it. It's a lot of technical information, and it might seem confusing at first, but of course we're going to go through it one by one and explain it all in detail so we know exactly what it all means. And this information is actually very important for us to understand, even when we're doing something as seemingly simple as printing text on the screen. So let's just go through this one by one, and some of this information will be the same as in our previous slide. For example, we still have our green outline tile map area here, which is made up of video locations that we're going to populate with pointers that tell us which characters we want to exist in these different locations in the tile map. And then we have our visible area here, just as we did before, which is 640 by 480 pixels, or 80 by 60 characters in size. But now let's go through these notes that I have on the right hand side here. And so here it says Tilemap Layer 1 Defaults. Now if you remember back to the beginning of this video where we talked about the different layers, where we have the background layer, which kind of represents your tabletop on your desk at home, and then we have two layers above it, layer 0 and layer 1, where layer 0 is below layer 1. Well, in today's video we're going to be using layer 1 in our demonstrations, and the reason we're going to be using layer 1 is because it's automatically configured on the Commander X16 in the perfect mode that we need it to be configured for displaying our text. And you can see I'm just going to jump ahead here a little bit to point out this point number 3 that says 16 color text mode. So Tilemap Layer 1 defaults, our layer 1 by default is configured in 16 color text mode, which is what we're going to be using today. And we're also going to be looking a bit later of how we can reconfigure these layers into different modes. The first mode we're going to be using is 16 color text mode, and so that's why we're going to be using layer 1 today, because by default it's already configured in 16 color text mode for us. Now let's go ahead and take a look at these other points I have listed here. The top one says VRAM, video RAM 128K. So let's talk a bit about the video RAM or VRAM feature in the Commander X16 computer. Now if you're familiar with normal personal computers, like for example the Sinclair Spectrum computer, or pretty much any other personal computer that was released back in the 80s, maybe the Mattel Aquarius or whatever computer you happen to have, typically the way the memory in a personal computer would work is there would be two kinds of memory installed. There would be RAM memory, which is random access memory, that would store our program that we create, as well as there would be ROM memory, read-only memory, which would store built-in routines that the computer uses to operate. And if you don't happen to be familiar with the architecture of 8-bit microcomputers, you may want to go back and watch a video that I made where I explained how the architecture works in an 8-bit microcomputer. But that's essentially how they would normally work. There would be ROM memory and RAM memory, and then when you wanted to access or modify any values in the random access memory, you would simply access those memory locations directly. However, with the Commander X16 computer, it works a bit differently. So one cool thing about the Commander X16 computer is that it contains its own separate memory called video memory, or video RAM, known as VRAM for short. And the way it works is the Commander X16 computer, as you may already know, has a separate circuit board inside of it called the VERA board, which stands for Versatile Embedded Retro Adapter, and that board is used to display the images that the computer will show on the screen. And this circuit board, this VERA board, has its own dedicated video memory or video RAM installed on it. And so that's what this VRAM note here is referring to. It's a separate VRAM memory installed on that VERA board. And the Commander X16 computer has 128K of video RAM installed on this VERA board. And the great thing about that is that the computer doesn't have to share the memory between the processor and the video circuitry in order to display images on the screen. The video circuit board inside the computer has its own dedicated video memory or video RAM, which it can use for displaying images, which is really cool. And as I just mentioned, this video memory is separate from the internal computer RAM, which would be used for storing our program that we create. And now let's take a look at the addressing that we would use for this video RAM memory. So you may be already familiar with how you would typically address memory locations in an 8-bit microcomputer, which may have a 16-bit address bus. Well, a 16-bit address bus in a microcomputer means it can access 64K of RAM. And you can see here, as I just mentioned, the Commander X16 computer has 128K of RAM. So that means it's going to need more than 16 bits to access all those memory locations. In fact, it's going to need an extra bit, which is why it uses 17-bit addressing And we're going to be taking a look at this in detail, of course, later when we actually create our program. But I just want to give you a heads up right now to be aware that it's not so simple to access the video RAM in the Commander X16 as it may be in a normal personal microcomputer from back in the 80s, where we would access those memory locations directly. In this case, we need to use 17-bit addressing, which makes it a bit more complicated. And when you do use 17-bit addressing for 128K of RAM, these are the addresses that you'll be using. And it says right here, address 0 to address 1FFFF. Those are the different addresses in the 128K of video RAM. And we'll be looking again at this more in detail later. Alright, so now that we've been taking a look at the tile map, which we should understand now is actually a section of the video RAM which is made up of a bunch of addresses, and these addresses are going to contain values which are actually pointers to the patterns for the tiles or characters that we want to be stored in those particular locations to be printed on the screen. So we just need to understand that there is a difference between the tile map and the actual tile patterns that are stored in memory. Remember, in the Commander X16 we are not storing direct values that relate to particular tile patterns in the video RAM tile map, but rather we're storing pointer values that are pointing to tile patterns that are stored somewhere else in the video RAM memory. You can see here there's a note that says layer 1 tile map goes from address 0 to address 03FFF. So this green outlined area here, which is the tile map, this is the area that's going to contain all the pointers to whatever characters we want to appear in the tile map, and these addresses range from 0 to 03FFF. So these are the addresses in video RAM that are reserved for the layer 1 tile map in this example, and we're going to find out, of course, how to store the different values we need to put in that tile map to point to whatever patterns we want to show up in those locations in the tile map. And again, as we mentioned before, layer 1 we're going to be using in 16 color text mode, and that gives us 128 by 64 characters to work with, and each of these characters are actually tiles, and these tiles are made up of 8 by 8 bit patterns, and we'll take a look at that in detail in just a moment. Now, one quick note before we take a look at these tile patterns is I want to take a look at this last note here that says 2 addresses per tile, offset, and color. So what does that mean? Well, I just mentioned that each of these video RAM locations in the tile map area needs to store a pointer to whatever character pattern we want to show up in that location. Well, there's actually 2 different values we need to store in the video RAM tile map addresses for each character that we want to exist in each location. So the first value will be a 1 byte value that will point to the pattern we want to show up in that location. So it will point to the actual character, and this might be referred to as a character offset. And again, this will indicate which pattern we want to show up in that position in the tile map. Now, the second byte that we need to store would be a byte that indicates the value of the color that we want that character to show up as. So now we're just going to take a quick kind of preview at a section that we're going to be looking at later in more detail, which is the configuration section. But now we're going to take a look at one of the configuration parameters that we can use to explain how we store these character offsets and color values in order to populate our tile map. So here now you can see on the screen I'm showing a page on the internet which is taking us to a GitHub page which is titled Vera Programmer's Reference, and this gives us all sorts of information about that Vera video board in the Commander X16 computer and how we can actually use it and configure it the way we need to. So I'm just going to scroll down to the section where it shows us about the values we need to look at for populating our tile map with the values for pointing at our character and also for indicating the colors we want to use. So if I scroll down here, right here you can see there's a section titled Tile Mode 1 bit per pixel, or 1 BPP. That's what BPP stands for, bits per pixel. And here it also says 16 color text mode, which is the mode that we're going to be using for displaying our text characters. So here it shows the 2 different byte values that we need to use in our tile map for each character that we want to store there. The first byte here is called character index, and that is the pointer that we discussed that is going to point to the pattern for the character we want to show up in that particular location in our tile map. And then our second byte here has actually two different sections to it. You can see it's split up into two 4-bit values. So bits 0 through 3 here, bit 0, 1, 2, and 3, they are what's referred to as the foreground color. So they would be a value that would represent the color of the ink or the foreground that we want that character to show up in. And then the high 4 bits here, bit 4, 5, 6, and 7, those values would refer to what background color or paper color we want the character to show up in. And as you can probably guess, since we're using 4 bits per color, foreground color and background color, since 4 bits can have 16 different unique values, then that means we have 16 different colors available to us for each of the foreground color and the background color. So these are the two separate bytes we need to store in our video RAM tilemap addresses. Alright, so we'll go back to our other slide here now, and we'll see exactly what we mean by that and where we need to store those values. So if we take a look over here at the top left-hand square in this tilemap area of the video RAM, you can see here it has an address of 0 showing on my diagram here. So address 0 in VRAM or video RAM would be where we want to store the first pointer location to whatever character we want to appear in that top left location of the tile map. And you can see here there's another label that says character index 1 bit per pixel. Now 1 bit per pixel, it simply means that there's 1 bit per pixel of the pattern for the character that's showing up there. So when the bit is turned on, then that pixel is turned on. If the bit is turned off, then the pixel is turned off. And we'll see that in a moment when we take a look at the actual patterns for one of the tiles. So address 0 in this case would contain our pointer to wherever our pattern is stored in memory for whichever tile we're interested in showing up in our tile map. And then the second address, which in this case would be address 1, would be the second byte, which would indicate what color we want our tile or our character to show up in. And again, the 4 low bits of that byte would indicate the foreground color, and the high 4 bits would indicate the background color. So that is what is meant by this note over here that says 2 addresses per tile. The first byte would represent the offset, which is the pointer to the character pattern that we're interested in. And then the second byte would represent the color that we want that character to show up in. Okay, so now let's take a look at the actual tile patterns themselves and see how they get stored in video RAM as well. So the tile map we just took a look at is stored from address 0 down here to address 03FFF. And since there's 2 bytes stored per character or per location, with the first byte being a pointer or a tile offset, and the second byte being the color value, then of course, since this is the last memory address in the tile map, then it would store a color offset, which again is 1 bit per pixel in this case. So now let's go ahead and take a look at the tile patterns themselves, which are stored in a different location of VRAM. And where are they located? Well, it says right here, they are stored at address 1F000. And here it says @symbol. So what does that mean? Well, let's take a look again at the characters that are stored in the Commander X16 computer. Alright, so here we can see the different characters that are stored in the Commander X16 computer in video RAM memory. So the patterns for these characters are already stored in VRAM for us, and of course we can use them for printing on the screen if we want. And as we're going to see when we actually create our program, the way we need to print those on the screen is by storing them in the tile map, of course. But before we do that, let's take a look at these character patterns and see exactly how they get stored in memory. First, let's take a look at this note at the top here that says bit patterns stored starting at 1F000, which is what I just pointed out on the other slide as well. And here again it has that note that says @symbol. And so you can see here the very first character in this grouping of tile patterns is in fact the @symbol. And so in this case, we're not actually going to be interested in the specific address here, 1F000, when we're populating our tile map, because remember we need to put a pointer to these patterns to indicate which character we want to display in our tile map, right? But we're not going to be indicating which exact address that pattern is stored at least not here anyway. In this case, what we're going to be doing is using these values here on the left column and the top row And those hexadecimal values are going to make up our pointers that we're going to populate our tile map with to point to these characters. So for example, if we wanted to point to this @ symbol, then our pointer would be 0, 0. If we wanted to point to this heart symbol, then our pointer would have a value of 5, 3, going from the left-hand column to the top row there. And let's say we wanted to point to maybe this asterisk symbol over here, then that would have a pointer value of 2A. So that is how we work out the pointer values. We simply look at this chart and we can see what the pointer values are needed to indicate which character we want from this grouping of characters. And if we go back to our other slide now, those pointers we just took a look at would be what is known as this offset here. So this tile offset value would be whatever values that we take from the other slide that we just looked at, which indicates the pointers to those different characters. So those patterns we just looked at are stored, as we mentioned, beginning at address 1F000 in the Commander X16 video memory. And now let's go ahead and take a look at a pattern for a tile. Here you can see on the left there's a pattern for a tile, which is an 8x8 character. So each character that we're using in this particular mode is made up of 8 bits by 8 bits. And of course 8 bits is a byte. So that means that one character is made up of 8 bytes going from top to bottom. So in this case we have a smiley face character here that we've got programmed, and there's the pattern for it on the left, and here are the binary values for it for each pixel that is either turned on or turned off. The pixels that are turned on have a binary value of 1, and then the pixels that are turned off have a binary bit value of 0. And these groupings of 8 bits form a byte, of course, and then the decimal value for that byte is in this column here. So for the top row, this binary value would convert into a decimal value of 60, which would convert to a hexadecimal value here of 3C under this hexadecimal column. And then here you can see the addresses where these different bit patterns would be stored. So this is an important concept to understand, which may or may not be confusing to some people, which is the pointers that we're using to point to those characters right here. Remember, these characters, we need to have pointers to tell us which character we're interested in. So for example, if we're interested in this heart character here, and we want to use a pointer value of 5, 3, well, 5, 3 is not pointing to the entire character, but rather it's pointing to one specific address in memory. And if we look at our pattern again, right here, in this case, if we wanted to point to this happy face character, we would use a pointer that points to the first byte in this pattern. So in this case, the first byte in this pattern would be stored at address 1F000, which is actually the first character in our character set. If we look back here again, you can see there's a note that says these characters begin at address 1F000. So if we were to reprogram this @ symbol, for example, into a happy face, then these are the addresses that those pattern bytes would be stored at. The first byte would be stored at address 1F000, and then the addresses would just increment up until the last row here at the bottom, which would be stored at address 1F007. Although when we look at our character set here, the pointers on this chart point to individual characters. Internally in the system, what they're actually pointing to is the first address of the pattern for that particular character. And back on this slide again, that is what this note here means, that the patterns are stored beginning at address 1F000. So just keep in mind that the tile patterns are stored in a different location from the tile map addresses. The tile map in this case ranges from address 0 to address 03FFF, and that would be made up of character offsets and color offsets, whereas the actual tile patterns are stored beginning at address 1F000. So now let's take a look at these last two notes here. The first one says 8-bit tile offset 256 tiles. So what does that mean? Well, remember those tile offsets that we discussed up here. Right here we need to put an offset into our VRAM to indicate which tile we're interested in. And remember, these are the offset values here. Well, you can see since these offset values are 2 hexadecimal digits, 2 hexadecimal digits represents 8 bits or 1 byte, which means that the maximum number of different characters there can be would be 256. And they would have character offset values or tile offset values or character index values, whatever you want to call them, ranging from 00 to FF. And that's what this means here. Since these are 8-bit tile offsets, the 8 bits can represent one of 256 different values, meaning we can have 256 different tiles. And then our final note here says 8 bytes per tile, 8 by 8 pixels. Well, that goes back to the pattern we just looked at right here. In this example, you can see that one character does have 8 bytes per tile. So this is a tile. It has 8 bits by 8 bits. 8 bits, of course, is a byte. So each line in this tile pattern represents a byte. So an entire tile pattern, which is 8 bits by 8 bits, would be made up of a collection of 8 bytes. Okay, so now it's time to take a look at the color palettes, which will show us what colors we have available to us to print our characters that we're going to be displaying on the screen. So the way the color palette works in these text modes on the Commander X16 is there are actually 2 different modes that we can use. And if we take a look at the notes here on the right side, the top note here says 256 colors in total, and it says ink on 0. And I'll explain what that means in a moment. But first of all, let's take a look at the image on the left here, which shows what the default 256 color palette is in the Commander X16 computer. And these colors can actually be reprogrammed to whatever shades of whatever colors you want. These are just the default ones that happen to be programmed in the computer to begin with, but you can change them if you like. So in today's video, we're going to be using 16 color mode, which it says here uses the top row of colors. So as you can see here on the top row, this square on the left looks like it's black, although it's not actually black. It's actually a transparent color, which is mentioned down in this bottom note here. Over on the right, it says first color is transparent. So we're going to be looking at in today's video how we can actually reprogram this transparent color to be whatever color we want. So remember how we were discussing about the concept of layers at the beginning of the video, where we were using an analogy of using clear plastic sheets as the different image layers on this computer, and then the very bottom layer, which is the background layer, would be considered such as your tabletop at home, where you lay these clear plastic sheets on top of your tabletop, and then whatever color your tabletop is would show through those clear plastic sheets. Well, the tabletop in this case would be the background layer that we discussed earlier, and the color that that background layer is will be whatever color we have programmed for this transparent color in the top left of this palette shown here. So we can actually reprogram this transparent color to whatever color we want, and then that transparent color will actually be the color of the background layer. But going back to this top note here that says 256 colors total, ink on 0. So although we're going to be using 16 color text mode today, I just want to give you a bit of a quick explanation of what 256 color mode looks like, because we can actually try that out in today's program as well if we like. So going back to our Vera Programmer's reference page here, I'm going to go down to the section that talks about the color palette, which is actually way down at the bottom here. There you go. You can see the color palette section here. And here it says, this palette translates 8-bit color indexes into 12-bit output colors. The palette has 256 entries, which I just mentioned. There are 256 total colors, which you can see here. And the top left color here, which is shown as black, is the transparent color. And here is how these colors are actually programmed in the computer. So the codes for each of these color shades are actually programmed into the computer in certain memory locations, and they're programmed using 2 bytes per color. And the first byte here, which is shown as offset 0, contains the values that represent the green and the blue aspects of the color. And then the second byte here, which is shown as offset 1, contains 4 bits which represent the red portion of that color, and then the top 4 bits for that byte are not used. And let's take a look at where these colors are actually stored in memory. And to do that, I'm just going to scroll up to this section here, which is labeled VRAM address space layout. So remember how we mentioned earlier that the VRAM or video RAM in the Commander X16 computer has addresses ranging from address 0 to address 1FFFF. Well, this little chart here shows you what the different addresses are actually used for and how they are allocated. So here you can see address 0 to 1F9BF is allocated as video RAM. Addresses 1F9C0 to to 1F9FF are allocated for PSG registers, which are programmable sound generator registers. These addresses at the bottom here, ranging from 1FC00 to 1FFFF, are where the sprite attributes are stored. But here you can see this range of addresses from 1FA00 to 1FBFF. That is where the color palette is stored. So each color in this palette, and there are 256 colors, each color takes up 2 memory addresses starting from address 1FA00. And the reason that each color takes up 2 addresses is because, as we just looked at, each color is made up of red, blue, and green components, and it takes 2 bytes to represent those different red, blue, and green component values. And here you can see, since the palette begins at address 1FA00, that is the first address of that transparent color in the palette. So down here again, if we look at our palette, this black color here, which is actually the transparent color, is programmed into address 1FA00 and 1FA01. So if we go in and change the values in those addresses, which we will do in our program a bit later, we will actually be able to change the color of this transparent color, which will be changing the color of the background layer as well. And I'll just show you this sheet here where I've made kind of a summary of the color palette information, where it says color palette. Each color takes 2 bytes, and these are what the bytes look like. So the 2 bytes in memory, they would obviously take 2 memory locations, and the first memory location would contain this byte here, where it contains 4 bits for the green component and 4 bits for the blue component, and then the second byte in memory would have the 4 top bits which don't do anything, and then the lower 4 bits would represent the red component of that color. And then of course the value of these 2 bytes together would go into making up whatever shade of color was represented by that particular location in memory. And again, you can see here that the beginning address is 1FA00 and the last address is 1FBFF. And if we take a look at my note here, it says first color at address 1FA00 and 1FA01, because remember each color requires 2 bytes to represent the color shade. It says the first color is actually transparent, and it says background color behind all layers. So as I mentioned before, the background layer is the lowest layer, it's the bottom layer, and the color of that background layer corresponds to the transparent color, and we can change that color if we want by simply changing the values that are stored in these 2 memory locations here, 1FA00 and 1FA01, and we will be doing that in our program later as well. Now going back to my slide here, our second note says 16 color text mode top row. So as we mentioned before, today's video will be focusing on using 16 color text mode, which means we only have the top row available to us, which is these top 16 colors here. And remember how we described populating our Tilemap memory addresses earlier? Well, these are the colors that we're going to be using for populating our Tilemap. And just as we were populating our Tilemap using pointers to the character patterns or the tile patterns in memory, similarly we're going to use pointers to these colors as well. And so in this case the pointers would range from 0, which would be the transparent color, up to 15, which would be in this case this gray color. So here we have 16 colors we can choose from, and if we take a look at our other page again, we took a look at these bytes earlier when we were talking about how to populate the Tilemap entries, where the first byte in the Tilemap would be a character index to indicate the pattern for the character we want to display in that location of the Tilemap, and then the second byte would represent the color that we want that particular tile to show up in. And we mentioned how the 4 low bits here, bit 0 through to bit 3, represent the foreground color or the ink color, and the 4 high bits here, bits 4 through bit 7, represent the background color or the paper color. Now keep in mind that this format here is for 16 color text mode that we're going to be using in today's video. But before we move on to that, I just want to briefly explain to you how this 256 color text mode works, because we do have 256 colors in our color palette, and we can use all those 256 colors if we want. And I just want to show you how we would do that. So similarly to how we would use 16 color text mode, we still need 2 bytes in our Tilemap for each character. The first byte represents the character index, or the actual pointer to the character pattern that we want to display. But in this case, the second byte doesn't have a foreground and a background color with 16 possible values each. In this case, it only has a foreground color, which represents the full byte value, which means we have 256 possible entries we could use to specify this foreground color. But as you can see by this note here, it says each bit in the tile data specifies 1 pixel. Well, that's just what we discussed earlier. If the bit is turned on, then the pixel is turned on. But this note here, it says if the bit is set, the foreground color as specified in the map data is used. So if that particular bit is turned on, meaning that particular pixel is turned on, then it's going to be displayed in whatever foreground color or ink color is specified in this second byte here. So then what will the background color be if we're only able to specify the foreground color? Well, it shows it right here. It says otherwise color 0 is used, transparent. So what that means is when we're using 256 color mode, we're only able to specify the foreground color, and then the background color for each character will automatically show up in whatever the transparent color is programmed as, or whatever the background layer color is programmed as. All right, so let's go back to our slide here, right here, and we'll take a look at the rest of our notes. So 1 bit per pixel, we mentioned if the bit is turned on, then the pixel is turned on, and that's going to be displayed in whatever the foreground color is specified. The tiles that we're using today are 8 by 8 character tiles, so they're made up of 8 pixels by 8 pixels, as we took a look at the pattern earlier. Now this next note says 2 bytes per color. Well, that's what we looked at earlier in how the colors are actually programmed into the palette, where each color requires 2 bytes in order to specify the values for the red, blue, and green components. Now here's a reminder of the addresses in video RAM or VRAM where these color palette values are actually stored. They're stored in addresses ranging from 1FA00, which is actually the transparent color, through to 1FBFF. And just remember that each color requires 2 bytes to specify its value. So in this case, if we wanted to, let's say, reprogram the transparent color, then we would need to reprogram the value at address 1FA00 as well as 1FA01. And then finally, our note at the bottom here just says the first color is transparent, which as we can see here in the top left corner, that is the first color or the transparent color. Whether we're using 16 color mode or 256 color mode, the first color is always going to be the transparent color, which, as we mentioned earlier, can be reprogrammed.